Greetings. The contents of the previous video was intended to be a preliminary for the topic of this lecture, which is going to be about a relation between exponential function and log function. Now, I'm going to bring one or two examples from the previous lecture for a kind of better comprehension of this lecture. Okay, then let's start, shall we? Now, 2 times 3 equal to 6, and 6 divided by 3 equal to 2 are equivalent on one hand and inverse of one another on the other. Now, they are equivalent in the sense that they are saying exactly the same thing, but in different way. They are inverse of each other, as one of them undo the work of the other one. So now let's make another example. Let's make algebraic example. Y equals to 3x and x equals to y over 3. They are equivalent on one hand and inverse of one another on the other. So let's see what that means with the graph and the chart that I have made. Now here, if I may, I also may I hope that it is good enough for you to let me zoom it, if I may, so that it can be a better seeing that. Okay, then I hope it is more clear. You can see that I have written the symbols large enough so that you can see it better. Okay, here, the chart that I have made, y equals to 3x, I have given the value of x. I have selected my x from where? From horizontal axis. And this is the chart I have got. Now, with respect to this rule of correspondence between x and y. Now, in this chart, I have selected my values from vertical axis. With respect to this rule of correspondence between x and y, which is exactly same as this, no difference. So the rule of correspondence between x and y here and here are the same. So if the rule of correspondence of them are same, their graph must also be same. Let's see if this is the case or not. Now, if you like to write, then you can always pause the video and take a note if you'd like to do so. Okay, here the graph of y equal to 3x, as I have already mentioned, I am selecting my values from the horizontal number line, and when x is 1, for example, y is 3, when x is 2, y is 6. And the graph has been sketched, and you are very familiar, a slope is 3, and I'm not going to go through that one, how that was sketched. Now, look what happens if I write this one, x in terms of y. How does the graph of that one will look like? I have also graphed that one, you can see. I guess I hold it with hand so that, well, maybe not. Okay, here, as you notice, I have selected my values from the vertical number line, from the y-axis, and look, when y is 6, with respect to this rule of correspondence between x and y, the x will be 2. When y is 3, the x will be 1, exactly like previous one. Now, I already mentioned in the previous lecture that this also is used, the very same primitive idea is used in calculus when they are talking about delta epsilon definition of limit, the tolerance interval that they are talking. So they go from the y-axis to determine the interval on the x-axis such that will hold. I'm not going to go through that. It's not a lecture in calculus. Okay, now let's see the relation of these two now with respect to if I, let me see. Now suppose that what I do, as I have done it in the previous lecture, but no, I don't need this one. No, in this one, what I do in the previous lecture, if I rotate this one 90 degrees clockwise or counterclockwise, and then reflect it, the graph that I see, that I have it here, in fact you can see that, that is the inverse, the relation x equal to y over x is the inverse of the y equals to 3x. That is the graph of its inverse. If I write y instead of vertical axis, I rotate that and use it as a horizontal axis, and then treat that one as a horizontal, giving the value from horizontal axis, then this graph comes out. As you can see, this graph and the previous graph, they are not identical. This and this are not identical, as you can see, but they are inverse of each other, in the sense that one of them will undo the action of the other one. So when we go to log and exponential, we see exactly the same thing is happening. Are you with me so far? Okay, now let's see what start the main topic of this lecture, and that is about exponential. So let's see what exponential function is, or we can possibly define it. Now exponential function are a function in the form of y equal to f of x is a function of x equal to b to the x, where b is a constant number. You know what that means, like 7, 8 is a constant. 7 doesn't become 6, 7 doesn't become 8. 7 stays 7 all the time, so we call it constant. So b is a constant number, and x is what? Is any number, any real number. Now I say it's a constant number. When I use the word number, it always means real number. So the question will raise, what kind of real number b can be? Now the answer, just to give you the idea of the question, is very interesting, because you are the one who are supposed to really think about that. Now, can b be a negative number? I want you to think about it, contemplate, and see if you answer the question. It's very, very elementary. Yes or no? So now, I take cases for b. Well, maybe I give you the answer already. I tell you b cannot be negative. So maybe I change the phrase this way. B cannot be negative, then find out why b cannot be negative. It's a constant number which is 0 or positive. Now, the value of 0 and 1 are trivial, those cases. So we don't have to even mention it. So the two cases that we take for the value that b can have will be between 0 and 1, and values bigger than 1. And we discuss that one and see what is the real difference and what do they have anything to do with logarithm. All right? Okay, then you are familiar with this one. I'm glad with this. Now I have written the cases that I already mentioned, that for those of you who wish to take maybe some notes. So you are welcome to that. Okay. Now I'm taking the case that I'm just comparing the case of b between 0 and 1 and b greater than 1. Now this is a typical generic graph when the base is between 0 and 1. When the base is between 0 and 1, this is the kind of graph you will notice it. And look at that, I have already marked the intersection with the y-axis. And you will see that the other one has exactly the same intersection. This point is important in the log and exponential functions. Okay, again, this is a typical graph of if the base is a number between 0 and 1. So you can select some numbers for yourself, 1/2, 1/3, 1/4, and so on, and sketch the graph. You will see a graph that looks like this in general. Okay, then, now, if the base, the b, is a number bigger than 1, then this is the typical or generic graph that you could expect. This is the way it looks in general. And as you notice here also, the 0, 1 is also hitting intersection with the y-axis is between 0 and 1. All right? Okay, then we are done with this one. Now, going back to the examples that I brought up first, y equals to 3x, which is equivalent to x equals to y over 3. In this case, y is written in terms of x. In this case, x is written in terms of y, but the rule of correspondence between the two remains the same. Now, this one, what we did, the way that we obtained this one, we divide both sides by 3. Now the question will come that in there is some noise here. My apology for that. Now here these two are equivalent, as I have said. We could use algebraic manipulation to obtain this from this or this from that. Now the question comes that what about if we have expressions that we could not use algebraic manipulation to create equivalent equations? We could not, there are cases also we could not separate x and y so that we can write x as a explicitly in terms of y. Then what do we do in those cases? Again, I repeat myself here, we could do algebraic manipulation to bring about equivalence between them, but what if we couldn't do that? Okay, we are going to discuss that one as well, what we could do in that case. Now here comes the log and exponent impact. Here I have the chart again. You are welcome to write it if you wish. Let me also write it this way. Now here I have written y is as a function of x in this form, and I have the chart of that, which is in reality is graph, because graph is a set of points. So this is the graph of that. And now I am saying that previously I selected I selected my numbers from the vertical axis, but the graph ended up to be identical. Now here I'm selecting the values from the vertical axis, and the graph is not identical. Look at that. When x is 0, y is 1. Here, when y is 0, x is 1. That's good, fantastic. Now here, when x is 1, y is 2. Here, when y is 2, x is not 1, x is 4. You see that? Here, when x is 2, y is 4. Here, when y is 4, x is not 2, x is 16. So these two are absolutely two different charts, and they give two different graphs. So these two are not anymore equivalent. But are they inverse of each other or not? That's what we are going to discuss about. But we know for sure they are not equivalent. They are not giving the same the same graph. Okay, then now let's go to the same example I have. No, excuse me, I have that one. I go to this one. What I just said, I have put it in writing, so you can write it if you wish. Let me hang it here. Now here, y equals to the x, I already mentioned y equals to 2x is not equivalent to x equals to the y. Here we cannot apply algebraic manipulation in order to express to express x in terms of what? In terms of y explicitly, as I have written here. Then how do we express the inverse of that? How do we express the inverse of y equals to 2 to the x? Y equals to 2 to the x is a one-to-one function, one-to-one correspondence in fact. Therefore has inverse for sure, and its inverse is a function. We know that for sure. So the goal is to find a rule of correspondence, to find a functional notation to represent the inverse of this exponential function. That is the goal of this lecture. We are going through all of this for preparation. Okay, then now let me go to this handout again. You are welcome to answer. Now here, how do we express the inverse? Now I have written the answer for you. The answer is this. You say x equals to 2 to the y. We are not, if we select our y from the vertical axis and determine the corresponding x, is not going to be identical to the y equals to 2 to the x. We already talked about that. I'm repeating myself. Now, to consider this one as an inverse of the y equals to 2 to the x, we have to select x as the independent variable and ask this question, and the answer of the question will be will give us the data that we need for the inverse of y equals to 2 to the x. Now what is the question? We will be asking that x is given, x is for example 8, then we are asking the question, what kind of number, or what is the number that if 2 raised to will produce x? And that number we already know is 3. So the input of this function is 8. The output of this function is the power that 2 should raise to in order to give you x. And that number will be 3. In that case, in that interpretation of the y here that is written, then we are talking about the inverse of what? Of the exponential function. In that interpretation of y. Now, the question is that we are not used to this kind of notation from the time we are involved with, from let's say not grade school, but from junior high, that we start to talk about function and relation. We become familiar with them. We are using the notation y equal to something, and then we say y is a function of that something. Or we can write y equals to f of x, or g of x, or h of x, or something, whatever the independent variable to be. In this case, we are talking about x. Then we are talking about that, and then we write it in that form. But we are just not looking, doesn't look that well. And the student, they are not comfortable with this looking and asking, even though there is nothing wrong whatsoever with this notation. He's just asking the question in order to find the y. You have to say what number x should, what number 2 should raise to in order to give you x. The number that x, the 2 has raised to, that number is the value of the y. So again, it's a nice looking function, has input and has output. All right, now let me see what I have next. Well, what I have here, I have already mentioned it, and that is that 2 to the x is a one-to-one function. Therefore, what? Therefore, must have inverse, and the inverse of that is also a function. Now, the question is, how can we write that function as a y explicitly represented in terms of x? That is the goal for that. Okay, then this one you are welcome to write it. You can always pause and take notes if you need, right. Now here I have this graph Now, y equals to the y, excuse me, x equals to the y, I have made a chart here that I've already talked about. So that, for example, just to treat this one as a function and input and output. The input are these numbers and the output are these. So again, I repeat myself for the third time, that the output answers the question 2 should raise to the what power will give you x. The power that 2 should raise to in order to give x, that is the outcome, the value of the y. There is, again, I repeat myself for the fourth time, there is nothing wrong with this notation, but somehow it doesn't appeal in our eyes. So we want to see if we can represent it as a y equal to something. So that is going to be our intention. Let's see if we may succeed in that. Now, what I just said I have written, so you are welcome to take a note if you write them. And it's that what I wrote here. Now, the question that we are asking here, we want to adapt a notation to what? To be y equal to something. And that is exactly what the notation of log come from. So this representation, we show it in this form. So y equals to log base bx means exactly same this. As a matter of fact, in my time, when I was first exposed to the subject, I was changing this one to this form so that I could answer the question and better comprehend the subject. So what this notation is asking b. The input is x, for example, is 8, and the base is supposed, let's say, is 2. Then this is asking the question, b should raise to what power to give you 8? The power that b should raise to give you x, which is 8 I mentioned as an example, that will be the value of y, the outcome of the function. So this is a nice looking fantastic function and a nice notation we invented for that. Because it's not similar to y equals to 3x that we could do algebraic manipulation and write x explicitly in terms of y. We couldn't do that, so we came with this invention, with this notation. Okay, then log and the exponent end up to be what? The inverse of one another. Okay, then now let's see what this one I have written, what I'm talking about in this handout. Okay, then I'm saying that y equals log base b is a function. The value of y are the answer to the question y da 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 da. So you are welcome to write that one. I just said it orally. Alright? Okay, then now comes the moment of truth to see the relation graphically of a function and was and its inverse. Let's see if I can succeed that one. Now, this is the graph of a function of b is what typical that the b, the base is what, let me write it this way, that the base is what is bigger than 1. That is typical. Now, how does the inverse of that will look like? So from the previous lecture, the preliminary lecture, we learned that if we rotate this one 90 degrees and then reflect it, what we get is the inverse of that from the previous lecture. Now, I have done it, you can see that, but I have done the same thing. I have a copy of that. This is exactly the same as this. I have copied that one in this and see what relation this one has to the original function, which is this. Now look what happened. Something interesting happened. Let me see. Something interesting happened. And if I superimpose the axes, the vertical and horizontal axes on the top of each other, I hope you can see that, is the graph of that you can see. If I had the light under that, I could show you so that you could see through that. Unfortunately, it's not transparent, but the graph of that is this. hopefully you can see that is this. Now I have already sketched that one exactly same. I copied the same thing. I have copied the same thing so that you can see that, and I'm going to put it here for you so that you can see it for yourself. And look at this one. Lo and behold, fantastic. Look at that. This is typical graph of a function with a base bigger than 1, and this is the inverse of that. As I said, rotate and reflect. And the previous lecture we said why it works that way. And then these two end up to be mirror image of one another with respect to the line y equals to x. Meaning the composition of this function and this function, if we compose them, is identity, which means whatever you put to the composition function, the same thing comes out. So we call it identity. So this is the relation between what exponential and log function. So log and exponential function, in other words, they are what? They are inverse one another. They are not equivalent, but inverse of one another. Okay, then I thank you for watching. I hope this lecture was beneficial, and I wish you all prosperity and happiness. By the way, I have given the site link of the previous lecture in the comment section. So you're welcome to watch that one. Okay then, thank you for watching and have a great day. So long.